bonding is the molecular orbital theory. And the molecular orbital theory, as the name applies, goes over the entire molecule. Okay, the molecular orbital theory, or MOT, involves the atomic orbitals of atoms involved in bonding combine to form orbitals associated with molecules. So the electrons are delocalized into the molecule or throughout the molecule. So in this theory, we're actually taking it to a molecular level. A lot of the other ones, the valence bond theory started, but it still involved atomic orbitals moving to molecular orbitals, and it still left some of that in place. Whereas in the molecular orbital theory, we're going to see that the atomic orbitals do combine, but they form totally different critters. Okay, so these molecular orbitals reflect the geometry and characteristics of the molecule, not the individual atoms. So these don't look anything like the individual atoms. And what we get is linear combinations of atomic orbitals, LCAOs, that are a weighted average of the atomic orbitals as we solve them through the system. Okay? So when we look at molecular orbitals result from the atomic wave function, which, remember, Schrodinger combined the wave and particle nature, and so he took the wave function, which that Giffey center of psi, and in this case, it's treated as a wave, and you're going to have the interference. And when you have the interference, then you're going to have constructive and destructive interference. Destructive. That is so not spelled right. Destructive. Well, it was spelled right. I just couldn't read it. Okay, so the molecular orbitals that form are kind of the most interesting in some ways, and kind of the goofiest looking ones in other ways. So we're going to look at them, and if you treat them as wave functions, what happens is you're going to get an overlap in between. So the first overlap will be a sigma, and the electron density is concentrated between the two nuclei. That's constructive. Destructive means that you have no interaction between the two nuclei. There's a nodal plane in between, and this would be the anti-bonding orbital. So this one's the bonding because it's between the two, and this is the anti-bonding. Well, think of it this way. You have two pieces of paper and you want to glue them together. If you put the glue on them and you put the glue sides together, they'll stick, correct? And then you get your bonded pieces. What happens if you put the glue on them and instead of putting the glue sides together, you put the non-glue sides together? Then what you end up with is absolutely no bond. In the molecular orbital theory, we call this anti-bonding. So this is their slide. This is my slide, because there are a couple other things we've got to remember. Same rule applies. However number of atomic orbitals you combine, then you end up with the same number of molecular orbitals. So if we combine two s orbitals, so we have a total of 2 orbitals, we produce a bonding and an anti-bonding, so we produce 2 orbitals. If we start with 6, you're going to produce 6. Okay, so bonding orbitals are lower energy, so they're more stable. Because remember, the lower the energy, the more stable they are. These should have been more stable. Okay, antibondings are higher energy, and that means they're less stable. And when we talk about being higher energy or lower energy, basically the atomic orbitals would come out in between. So when you combine them, you actually drop below, and when you're anti, you're above. And the antibonding orbitals contains a node. Okay, remember a node is a zero probability of finding an electron. So here we combined the s orbitals. And s orbital plus s orbital, that's 2 orbitals. Wait a minute. If you combine the p orbitals, you have 3 p orbitals. So what happens is that there are 2 ways that you can combine the p orbitals. You can combine them as a bonding orbital. So here, when they end on overlap, here's your bonding orbital. Here's your anti-bonding orbital. And notice that the anti-bonding orbitals all have the little stars. And if you sideways overlap, you end up with the bonding and the anti-bonding. Now, because you have 3 p orbitals, here's 1. You can only end on overlap. The other 2, so 2 and 3, would produce the sideways overlap. They'll just be 90 degrees to each other. So you would end up, start with 2 orbitals here, 4 orbitals here. You end up with 2 orbitals over here and 4 orbitals over here. So basically, this is actually not that bad. And here's where, if you can't combine them, the book combined them. Here's your end on, here's your sideways overlap. And notice that you have 2 here, 4 here, 4 here. So you have to make them balance out. So what's it look like when you're actually trying to diagram it? Okay, so when you put it in here, these are your atomic. So remember, we drop down to our bonding and we go up to our anti-bonding. So technically, these actually disappear, but they're kind of left in to give you a reference to the energy, because this is the set point to go above and below when you get to the bonding and the anti-bonding. So that one was a little busier. This one is where it just has all the labels. So you have to have the anti-bonding and the bonding, and you'll have the 1s atomic orbitals that combine to give you. So if you combine 2 atomic orbitals, you get 2 molecular orbitals. If you combine all of the p's, so these are the s's and these are the p's. So you'd combine 3 p's from each one. So that's 3 plus 3 is 6. So we would have to produce 3. Now notice, remember, antibonding orbitals are designated by the stars. Okay, so this is the complete labeled form. On the exam, you will, again, since whether it's online or not, I give you a layout here. I give you a layout that is unlabeled, and part of what I ask you to do is label it. So you may be given a stripped out form, and this may have the number 7 in it, and you may be asked what does the number 7 in the diagram indicate, and it would indicate the sigma pi orbital from the 2 p's. Okay, because remember, these are all the p orbitals, and these are all the s orbitals. So notice we have a sigma with an s, and we have a sigma with p. We have a sigma star with an s and a sigma star with p. We also have the pi orbitals and pi star orbitals with the p's, because you have 3 p from each atom coming together. 3 plus 3 is 6, so you have to produce 6 out. So that brings us to the bonding order. Can't speak now. That is the net number of pairs bonding electrons in a molecule. So the net effect that this does is the bond order tells you the number of bonds that can form. And this is actually pretty cool because this tells you whether a molecule will form. And it's actually real simple. You count the number of bonding electrons, you subtract the antibonding electrons, and you divide it by 2. All right, so we're going to work several of these so you can see how this works. Again, I'm going to give you the diagram. We're going to work these in different colors. On this same diagram, I actually have it twice so that you can see the difference. And I may flip it back to do the O2 plus. I'm not really sure. I may actually do that one separately. So let's do nitrogen first. Nitrogen has 5 electrons and there are 2 of them, so we're going to look at 10 electrons. Now the same rules apply, Hund's rule, etc. So what we're going to do is we're going to start down here. This is the pi s bonding orbital. This is the pi star anti-bonding s orbital. This is the pi p bonding orbital. The sigma p. This is the pi p and the pi p bonding orbitals. This is the pi anti-bonding orbitals. This is the pi anti-bonding orbital. And this is the sigma anti-bonding p orbital. Now, in some graphs, you'll see where the pi bonding orbitals actually come a low energy than the sigma. I'm not worrying about that here. That's kind of above your pay grade. There are reasons why it does that. It has to do with why the 3Ds don't fill after the 3Ps, and they fill after the 4S's, that type of energy consideration. I'm not worried about that here. So I've labeled it so we have 10 electrons. So since I'm going to do the nitrogen and the fluorine on the same graph, I'm going to do the nitrogen to the left. So 1, 2, 3, 4, 5, 6. Hund's rule applies. 7, 8, 9, 10. So nitrogen here has this layout. So if we look at the bond order for nitrogen, then we're going to have 2, 4, 6, 8 bonding orbitals, bonding electrons, 2 anti-bonding orbitals. We're going to divide that by 2. So that's 6 divided by 2. So we should have a triple bond between the 2 nitrogens, which we know that we have. So we're good on that one. So let's change colors. So we're looking at something really different. To do the fluoride, that's 7 times 2, that's 14 electrons. We've got the same, we've already labeled all the orbitals, so let's get started. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So if we look at the bond order for the fluorine, then if we look at it, we have 2, 4, 6, 8 bonding orbitals, electrons, and then we have 2, 4, 6 anti-bonding orbitals divided by 2, so that's 2 divided by 2. So the bond order for fluorine is 1. So we know, based upon experimentation, etc., that fluorine forms a single bond and nitrogen forms a triple bond. So what molecular orbital theory is able to do is predict the bond order, single, double, triple, that occurs in molecules. So we're going to take that a step forward, and we're going to go ahead and do O2 plus separate, and again, sigma S, sigma star S, sigma P, pi P, pi star P. I'm not going to label both sides because I figure you can figure that out. So what we're doing here is we're counting electrons. So we have 2 times 6, which is 12. But we have a plus 1, so we're going to subtract it. So we only have 11 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if we look at the bond order here, then we would get 2, 4, 6, 8 minus 2, 3. 3? Yes. 3 anti-bonding divided by 2. So that's 5 divided by 2. So the bond order here would be 2.5 or 2.5 is the bond order for the oxygen. Again, just out of sheer entertainment value, let's go ahead and do a second one. What happens if we had O2 2 minus? So that would be 2 times 6, which is 12. We have a negative 2, so that's plus 2, so we would have 14 electrons there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in the case of this one, our bond order here for the O2 2 minus is 2, 4, 6, 8 minus 2, 4, 6 over 2. So the bond order here is 1. So the O2 2 minus would actually form a single bond, whereas the O2 plus is going to form a 2.5 bond. So I know you were told that you can't have half bonds. Well, guess what? When we talk about molecular, we're delocalizing the electrons over the entire molecule. So we have a little more flexibility with respect to the bonds because you're spreading it out over an entire molecule. In these cases, these are diatomics. And so it's more simplistic, but you can carry it out further. Now, I gave you a couple extra forms so that you can play with them and practice with them, but I'm not doing anything with them. Phases, atomic and molecular orbitals, it's worth looking at to understand the constructive and the destructive interference. Okay. There are a couple other properties that are explained by molecular orbital theory. Actually, diatomic is explained because of the bonding, but diamagnetic is when the electrons are paired, so they are repelled by a magnet. And you're like, wait, I've seen this before. Yep. Paramagnetic is you have unpaired electrons. So they're attracted to magnets. We looked at this before when we were doing electron configurations. And in electron configurations, we're talking about the atomic properties. And that works well for atoms, but some molecules are diamagnetic and some are paramagnetic. So you have to explain them using the electron distribution over the entire molecule, not just an individual atom. So we can't look at it from the viewpoint of just an atom. We have to look at it from the viewpoint of the molecules. So when we look at the energy diagrams, if you look at this one is unpaired. So this one is going to be paramagnetic. O2 has unpaired electrons, so it's paramagnetic. All the other ones have only exist with paired electrons, so they're all diamagnetic. Okay? And if you'll notice, you can look at the bond orders. So notice that neon over here has a bond order of 0. So what that tells you is neon cannot bond to itself or actually to anything else. And we know this because this is a noble gas, so it's actually got full shell. So it doesn't want to bond with anything. But this allows you to look at the properties across the molecule. Now, this is, okay, I think this is wicked cool. This is oxygen. This is liquid oxygen. And if you pour it between a magnet, it sticks to the magnet here. So it actually is magnetic. And one thing about liquid oxygen that I found out that's kind of interesting is if you go down the interstate, you'll see these little trucks. And they're hauling liquid oxygen. They're labeled. They're, I think, green and white usually. And, you know, they're labeled with the particular signs or whatever. But here's the trick. Liquid oxygen is shock sensitive, and it tends to stay together. So if the truck had an accident, don't go near it, because when the liquid oxygen pulls out, it acts like water in terms of it'll seep into the ground and stay in little pools until it evaporates off. And if you were to step on it, it's shock sensitive, so that it's very reactive and it would blow up. So it kind of acts like a little landmine. But I just think it's cool because you can pour it and it'll go lie between the two magnets. Okay, so what molecular orbital theory does is it will explain paramagnetic and diamagnetic molecules, which is different from atoms. So this allows you to explain properties. Now, one of the other things they show you is that if you take combining different atoms, which have slightly different energy levels, then the molecular orbitals are offset as well. I'm really not concerned with this. You'll be concerned with this later when you get to organic or inorganic, and this actually comes into play. I just want to point out that these look skewed because they're differing energy levels, so therefore you get slightly wonky, shall we say, molecular orbitals forming. Now, the other thing that's really cool is molecular orbital theory will explain resonance. So we said that ozone, remember, ozone had the moving double bond between the oxygens. And so we said that the true structure lay somewhere in between. And we talked about the fact that it was a 1.5 bond, and you're like, you can't have a 1.5 bond. No, you can't in valence bond theory or in VSEPR. But you can in molecular orbital theory. And what that allows this structure to do, it moves from a single bond and a double bond to the 1.5 bonds which go across the entire molecule. The same thing with benzene. We talked about the fact that if you have these double bonds that are moving around, the net effect is what I call the racing donut. You have a donut above and below the plane that allow the raceways to occur. So that allows you to look at different molecules. This is chemistry put to work, orbitals and energy. This talks about HOMO and LUMO, which is very critical in organic chemistry. And what it means is LUMO is the lowest occupied molecular orbital. HOMO is the highest occupied molecular orbital. And this gap in between these two positions allows you to measure the energy transfer. This is why some molecules will conduct electricity and some will not. They act as insulators because the gap is either too large and therefore it can't be made to jump, and you don't have a conduction band, whereas in other ones you will because the HOMO-LUMO gap is small. Now, chapter in review, one of the things you need to look at when you're reviewing in this chapter is you need to designate the different types. So we have VSEPR, we have valence bond theory, and we have molecular orbital theory. You want to classify these, which involve shapes, which involve hybridization, which involve properties of like diamagnetic and paramagnetic. Vesper and MOT did that, but valence bond theory didn't address that in any way, shape, or form. Now remember, we have three theories, to explain bonding because none of them work. Each of them explain individual bonding properties, associations, atomic, molecular shapes, whatever, but not one of them explains all of them. So that's why we have three theories along until somebody comes with a better theory that would explain all the properties. So as you look at these, look at how they're alike and look at how they're different, because you may very well be okay. You'll be asked questions about that as well. So this actually finishes out chapter 9, which covers all the material on this last test.